This is a more advanced video on how to prepare data and fine-tune speech-to-text models, transcription models, also known as audio-speech recognition models. Now, models change pretty fast in the machine learning world, but in voice, to some degree, Whisper remains a bread and butter based model that is quite useful if you want to have a transcription model that is tuned to your application. I'm going to talk about how you can tune it using Unsloth, which has now got support for fine-tuning. It's about 2 times faster than using transformers. And I'm also going to talk in detail about the data preparation and some specific tricks you can use to improve quality. I'll be working out of the advanced transcription repo or advanced audio. You can find it if you go to trelis.com/advanced-audio. This is a paid repo. You can buy lifetime access to it. If you want some free resources, there is a notebook from Unsloth. You can find it in the Unsloth GitHub repo that goes through fine-tuning. I'm going to build on this, and I'm going to add in quite a bit around data preparation. That's converting from audio into transcribed text that you can then create a high-quality data set from, like this. It's a bit similar to the previous video I made on this topic, but now introducing a few other data cleaning techniques. And I'll then take you through step-by-step the fine-tuning itself. So the first thing I've done is I've cloned the repo. You can see it here, Advanced Transcription. This is a repo that contains scripts on data preparation and fine-tuning, not just for transcription models, that's speech-to-text, but also text-to-speech, also speech-to-speech models, also diarization and turn detection. You can find more about that in the playlist in the Trelis Advanced Audio or the Trelis Audio playlist. Now, the most recent addition to this repo is using Unsloth for the fine-tuning and the corresponding data preparation scripts, and that's what I'm going to cover today. So we'll be working out of the speech-to-text folder here, and we'll be particularly leaning on this Trelis Whisper fine-tuning notebook, which is now updated for Unsloth. In order to run that notebook, I recommend using a GPU. You probably could train on a Mac if you had a powerful Mac, but really, for the cost involved, which is probably just a few euro, it's worth starting up a GPU. There's a one-click template. It is an affiliate link, but it allows you to get started very quickly. You can choose a cheap GPU like 40 cents an hour, this A40 here, and I'm going to call it Whisper Fine-Tuning, and I'm going to get that started. And what this one-click template does is we can check here, if we just go to Edit Pod, it's going to set a number of variables, including your GitHub username and your personal access token, which you need to set in Run Pod Secrets. It's going to clone the repo here, Advanced Transcription, and it's going to do some installs. So once you start up the pod and you go into Jupyter Notebook, things should be fairly set for you already. Now, it'll just take a few moments. You can see it's cloning right here, and then it will start up the Jupyter Notebook. And we're going to operate within the browser, so I'll be able to run most of this tutorial here within the browser. If you want a little more guidance, you can check the README. You'll see that the key notebook we're working on is this one here. There are other resources available if you want to take a look at the Voxtral model, the Kyutai model. I'll just briefly mention a few differences in these. Whisper is kind of the original speech-to-text open source model. It is right now probably performing a little bit less well than Voxtral. And so, yeah, Voxtral is not well supported yet by transformers or by Unsloth. I may consider doing a video on that. But also Whisper has just got better tooling. If you want to set up a server, you can run faster Whisper. You can set up a continuous batching server. That's covered in my video on Whisper Turbo. I won't cover it more in this tutorial. So I think Whisper still has some advantages, even though it may not be the absolute strongest model. There's also Kyutai, who have a series of streaming text-to-speech and speech-to-text models. I've already made a video on that if you're interested, and I'm considering making a video to fine-tune this. Kyutai is trained off of Whisper timestamp data, so it will not perform quite as well as Whisper, but it's a streaming model, so if you want to have very fast captions and you want to have one word at a time, it's going to be a lot more compute efficient than using a Whisper model. So I do see benefit in the Kyutai model here. By now, it looks like our pod is up and started, so I'm going to open it up here in Jupyter Lab. I'm just using the RunPod terminal, and I'll click in here to advanced transcription, speech to text, and then open up the notebook here. The first thing I'm going to do is make sure some of these system installs are done, ffmpeg, and then I'm going to change directory into advanced transcription and do a number of installs here. You'll notice that in particular, I'm installing Whisper timestamped. Whisper timestamped is a version of Whisper that additionally provides word level timestamps. Now, Whisper itself provides segment level timestamps. That's a number of words in a row. It'll show the start and the ending timestamp. You can also get word timestamps from Whisper. Those timestamps, if you turn on word timestamping, they're derived from the attention matrices that are within the Whisper model. It uses heuristics to assign words to timestamps just based on the logits of those matrices. And this works somewhat well, but what I found in practice is that it can leave out chunks of the transcript. And that's what motivated me to use Whisper timestamped, which has got a small model separate to the Whisper model that is used in order to do the alignments. There's actually an alignment model in addition to Whisper, and this makes it more accurate compared to using just the weights that are within the matrices of the Whisper model itself. I will show you just now, why am I even talking about this? Because we need to generate data. Our goal here is to fine tune a Whisper model for a custom application. And that means we need to have both audio and a clean transcript. And one of the easiest ways to generate a clean-ish transcript is to transcribe it using some other model and then review it as a human to correct any errors. We do want to, there's a reason why we want to have word timestamps as well, because it allows us to control the lengths of the chunks and make them more consistent. We're going to see that. It'll become apparent as I walk through the data preparation. But suffice to say, if you want accurate word timestamps, it's best to use Whisper timestamped, not just the Whisper model. And you'll see shortly the benefit of being able to do accurate word timestamps. Now, once all of these installs are done, I'm going to install Unsloth. And that's going to take a little bit of time to run. And when Unsloth is done, we'll be ready to move into the speech to text folder, set fast transfer, although I'm less sure this is relevant now that XCT is typically used for downloading from Hugging Face. And then we're going to set up here the some of the path variables. So I'll just go through this. The model we want to use for transcription is going to be Whisper Large v3. It's the strongest Whisper model, but we're actually going to fine tune Whisper Large v3 Turbo. v3 Turbo has got many fewer layers. It's a much faster model. It's a distilled version of the large model. It almost achieves the same accuracy, but not quite. But it's quite a bit faster and lighter. So it's nice if you fine tune this fast one, but you want the highest quality data possible when you're generating your data for fine tuning. And for that reason, when we transcribe our data initially, this is the model here that we're going to use. The language we're going to use is English. This is the abbreviation, and the task is going to be transcription. Whisper is able to detect which language you're using, but we need to specify in the training because within the data, you will have the transcript, and just at the start, there's going to be a token that indicates which language it is. So we need to have the correct label to indicate the language when we're going to put the data there. Now, I should just maybe say a few quick comments about the video layout here. The goal is to fine tune on a custom data set. The specific task that I'm going to fine tune for is to get a model to be able to pronounce words that it's unfamiliar with. And the way I'm going to do that is to take a number of AI type words or large language model type words, such as these here. Remember, Whisper is now a 2023 model, so a lot of the terms like GPT-5 or, these are even old terms from 2023, but the model does not know them because the cutoff point for Whisper is before these dates here. So what I've got is just a series of Yi34B chat. That's quite an old model at this point. But I've got a series of terms that occurred after the training cutoff of the model and therefore are not contained or not familiar to the model, and the model will not correctly transcribe these terms. So my goal is to generate a data set where I have audio, which is actually me reading out these terms, with a clean transcription. And you can see here my clean data. And this is then what we're going to use to do the fine tuning. So we want to fine tune our custom data set, namely specific AI terms. The first thing we need to do is we need to record some audio, which I have already done. I've recorded myself reading out some text that I generated. I just picked some terms and then I started talking about what these terms mean and recording myself. You can listen to a snippet here if you like. MMLU is a means of testing performance. Claude 2.0 is the latest Claude model from Anthropic. So this is me reading out text, and there's roughly about 2 minutes. I also have, this is the validation set. I have a test set that's roughly of the same size. Now, these are very small data sets. You would need larger data sets to get high quality, but you're going to see that even with these small data sets, we're able to get reasonable type of performance. So record some audio. Then the next step is transcribe the audio. Then clean the transcription. And you can use an LLM or human. And I actually recommend human. It makes a big difference. Then we're going to fine tune on that data. And then we're going to make the model ready for inference, including via a streaming server, well, a continuous batching server. So these are the tasks we're going to do. I have pretty much done the first one. So what we want to do now is we want to read in some audio. I have put the audio actually into this data folder. You can see here we have train.mp3 and we have validation.mp3. So I've got the audio. You could put in any files here that start with the word train, train dash, and that you could put multiple train files, validation dash, put multiple validation files. And we're going to now transcribe them with the help of Whisper timestamped. And then we're going to clean that transcription so that we can push up a clean data set, namely the one that I showed you right there. So once we have the data set pushed, which I will explain, we're just giving a name to the data set. We're then going to train the model, and we're going to train this model here. We will train it using LoRa adapters. So we're just going to train a small set of weights that will be attached and eventually merged into the base model. And then we will push that model up to Hub. I'm going to talk through now how we transcribe and how we clean up the data set, just while everything here is running. It looks like we're just waiting for Unsloth to run at the moment. So I've already said you put the MP3 files here. You can put in WAV files either, if you like. Either of them will work. And we're now going to transcribe. And to transcribe, we're going to use the Whisper timestamped model. But I want to show you, I'm actually going to run a little demo here where we use just a Whisper model, not Whisper timestamped. And I'm going to show you the different ways that you can transcribe. The first way is with true. So let's just run that. And if you set it to true, true means segment timestamps. And if you set it to word, that means word timestamps. So when you go through this, and this is a pattern that I kind of learned as I tried things, the first thing I did was I tried just transcribing with Whisper. The problem you'll see if you transcribe with Whisper is that Whisper will often give segments that are of very different length. So you can get a first segment that's maybe 80 seconds, then you get a next one that's 30 seconds, then you get one that's 20 seconds. Now, for the purpose of training, what you want are chunks that are less than 30 seconds because that's the input limit to Whisper. Now, it's a bit confusing why you might even get 80 seconds of transcription out of Whisper, and that's because the Whisper pipeline will actually overlay windows. So it will overlay windows and then it will combine the result of those windows into one single transcript. And that's why you get segments that can be longer than the window. But when you're training, you're going to have to still segment to be less than 30 seconds in your segments. And the problem, if you have a large segment, the problem is that you need to cleanly separate that into smaller segments. And ideally, you want to separate it at boundaries like the end of a sentence or maybe a long pause. You don't want to split it in the middle of a sentence because the model then, particularly if you start a training segment from a point that's in the middle of a sentence, it's harder for the model because it hasn't got the context of the words that come before. And a sentence is kind of a complete unit, so you really want to provide that complete sentence. So what the word timestamps allow you to do is they allow you to assemble your own segments that have a much more controlled length. Because if I have the timestamps for every word, I can lay the words out one after another until I get towards 30 seconds. And after I've run Whisper, we're actually going to move to Whisper timestamped. So I'll just get that moving here. If you want, you can test Whisper timestamped on its own, but we're anyway going to use it down below. So I'll be able to show you what the output looks like. And what I'm going to do is transcribe to get the word timestamps. And then I'm going to assemble those into segments of length that I would like to see. And I'm going to do that for the training data and for the validation. And I'll just show you up here loosely how that works. So if I go to, let's just say here, I can add in a new cell. Assembling, well, let's call it transcribing and assembling chunks. And the way this works is I start with transcribing word chunks. So I've got word chunks, and then add word chunks to form segments until I hit at least 20 seconds. And then once I get to 20 seconds, I say close the segment if I reach a full stop. Technically, it's if I reach a full stop or any of these other things, like a question mark, exclamation mark that indicates the end of a sentence, or a long pause. And then if I hit 30 seconds without a pause or full stop, then just force the end. So yeah, I get the word timestamps, I make these segments, and now basically what I end up with is these clean chunks that have got between 20 and 30 seconds of content within them. And I don't actually need then all the timestamps for the words. I just need the start and the end. But the benefit of having the word timestamps in the first place is that I can actually, on a granular way, create these clean segments. So what I'm hoping for is to create some transcriptions that are going to go into the raw folder here. This is the output of getting words from Whisper timestamped and then assembling them into those 20 to 30 second chunks. So you can see a 20-second chunk here. You can see here a 25-second chunk. Here's a chunk that's about 20 seconds. So all the chunks should be between 20 and 30 seconds. I recommend checking that these here are contiguous. What I want is I want to see that this here follows on from this. Now there'll be a small gap because there's the silence between the end here and the start here. But you want to make sure that there are no large gaps in the transcript where words were being missed, which unfortunately is what I saw when I used Whisper without using Whisper timestamped. Now notice how this is raw. It's raw because this should be Claude 1, Claude 2. So it's got some errors. It doesn't recognize MMLU. There's, let's see another example. DeciLM, that's DECI, but it's not familiar with that. So it says DESI. So there are a range of transcription errors. Nulltux 8x7BV1, that should be notux. So what we're going to do is take this raw transcript and just correct it. We should hopefully now have some transcription that I can show you. Yeah. So here, if we just use Whisper, this is using Whisper, not Whisper with the timestamps. This is the text that you get out of it. You know, it's got the errors because it's not trained. And here are the chunks. And in this case, it's giving a 30-second chunk, 12 seconds, 7 seconds, and then 78 seconds. So you could stick with these chunks and somehow break up the one that's longer than 78. But the problem is it's not easy to break it up if you don't have word timestamps, because if you just say, I'm going to cut this in half, you can't just guess that the time is going to be half to get to this point here, because the words are going to take different amounts of time. So actually, if you have these segments, it's very difficult to break them down into chunks of the right length. What you might end up doing is kind of truncating the end, but even then you don't know how it ends. So what I found is you kind of have to timestamp on a word basis, and that does allow you to then add them all together into a row. So this is Whisper. If you instead transcribe with Whisper timestamped, what you will get is you will get something on a word by word basis. And seeing as actually that's not printed, I'm going to just do it. I'm going to run here, Whisper timestamped. We're loading some data. We're using whisper.transcribe, which is the Whisper model here, loaded using Whisper timestamped. And what you'll be able to see is the difference in the output. It's going to show us a few of the words, and it's going to show us the timestamps. So here from Whisper timestamped, you've got, a similar transcription, but then you have all of the timestamps here for the words. So this is how I'm able to just keep on concatenating words until I get to 20 seconds. And once I get to that, then I will close it off once I reach the end of a sentence. And that's why, rather than having just these uneven chunks, you can see my raw VTT file is a lot cleaner. And I have this nicely laid out here. What I recommend from here, you'll be tempted to try and automate the cleanup, and I'll show you how you can try to do that, but it's very difficult, even with strong language models. The reason why it's difficult to clean this with a good language model is that there are two types of error. One type of error is a misspelling. For example, null tux should be no tux. And you can give the LLM a list of keywords, for example, this list of keywords here, which are all of the correct spellings, and you can ask the LLM to rewrite the VTT line by line with the correct spellings, and this you can fix. What you can't fix as easily is if the transcription itself is missing words. There's no way that you're going to be able to recover those. Also, if the transcription adds in extra words, if you give a line of text that has added words, there's no real way for a language model to know that there are extra words there. So this is a drawback of this kind of approach. One potential workaround where you could use an LLM, although I don't do this here, is to create this text in the first place, or to create this audio. I was reading out a transcript. So ideally, I would provide that transcript back to the LLM to basically fix this here. You could ask, why would you even use an LLM? Can't you just sub it back in? But you do need to have some smart segmentation, because the transcript I would have read from was just one big paragraph of text. So you need to decide where you want to chop that. And possibly there are ways that you could chop it deterministically by looking at the paragraph and by looking at this raw transcript here. For example, you could try and detect the end of this segment here and see if you can find that by a kind of find operation in the original paragraph. But if there are errors in the transcription, that probably won't be entirely robust. So you need something like an LLM or like a human to be able to make the match between the original transcript and the timestamp transcript, because ultimately we do need to have timestamps if we're going to be able to train. So yeah, basically two ways of doing it. One is just make the transcript like I have here, then human fix it. And then the other way, which you can try out a bit yourself, is take the original transcript, feed that in, and then on a line by line basis ask the LLM to fix it. And the third way, which I will show you here, but is not very robust, is to basically feed in a prompt where you feed in a line of the VTT file, and then you feed in some keywords like I've shown you here, and you ask the LLM to respond with the corrected VTT. And if you do this, and you can do it by loading an API key here, what you'll get out is, you will get out, this is my clean version here. So this is better than what the language model is going to do. I'm going to just call these clean just so I can temporarily keep them. And then I'm going to run this dataset cleaning, which is going to require me to set an API key. So it's going to install OpenAI. It's going to install python.env, just so we can write the API key temporarily to a .env file so that if we rerun the notebook, we don't have to keep rerunning it. And I'm going to get my API key here from OpenAI. So I'll just paste in that API key. And now I'll run the cell. And this is going to take in the raw file, and then on a line-by-line basis, it's going to pass it in. Now, actually, it's a little more sophisticated than that. If I want the LLM to fix this, I also give the previous line and the next line, just so it's not missing context, but I ask it to focus on fixing the intermediate line. And then on a segment-by-segment basis, it will go down and fix that. So you can see here it's correcting line 1 of 7. Should be 7 lines, 1, 2, 3, 4, 5, 6, 7. And it's going to do the same for the validation file. And then it's going to save them here as train.vtt, which we'll see appear now. And we can take a look. And you'll see it has improved. So if we look at the raw file here, Trixie is now spelled correctly, Trixie. We have some nice formatting for Mistral here, or Mixtral. We have MMLU. We have Claude now correctly spelled. So it is properly putting in the right words. But actually, if you listen to the transcript, it's not exactly the same. And I can just show you a quick example here. Now, what I would recommend is you listen to the transcript and fix it at the same time. So here's the training file. Let's just listen.
Spin. Self-play, fine-tuning that improves LLMs.
That's good.
Trixie, it's a form of fast inference involving sparsity. Phi2 is a model from Microsoft. Lightning Attention 2 is an alternative to Flash Attention. Mixtral 8x7b.
So that's good.
This is a mixture of experts model. Solar 10.7b is a Mistral model with some extra layers added in. OpenChat is a fine-tune of the Mistral model. Notux 8x7b v1. This is a version of the Mixtral model, fine-tuned. Gemini Pro is Google's best model, or perhaps not as good as Gemini Ultra. Microsoft Phi 2.
You can see here that these are, somewhat minor errors, but there are words missing. Like there were these words here that were completely absent. And actually, as you go further down the transcript, it's largely because I made audio that was not all that clean, which is probably not advisable. You should record more carefully without making hesitations like I did. But because of those hesitations, there are mismatches. And so when you go to the clean version, and this is just clean by me reviewing it carefully, you'll find that there are significant amounts of differences in the words. And when you do the training, if you train on something that's not human cleaned, I was getting, for example, word error rates of maybe 40%, whereas on the human cleaned one, I was getting word error rates of 20%. Now, word error rates will be fairly high because the data set is quite small in this case here. And I was also not using teacher forcing, which is something I'll comment on a little bit later. But broadly speaking, I saw big improvements by improving the sentence cutoffs, so making sure that I cut off at the end of full stops or sentences rather than the middle of sentences. Then 2, I found big improvements by doing a human review of the transcript as well, which, is somewhat unfortunate because it means the pipeline is a bit less scalable. But yeah, it just highlights the importance of having high quality data, and smaller high quality data is probably better than larger low quality data. So we have now our clean data. I'm going to delete these files that were created by the LLM, and I'm going to use the ones that I have from earlier for the training. These are the ones that I manually reviewed. And with that, we will move on to creating a data set and then training on the data set. So here we are going to create the data set. This is not anything very fancy. What I'm doing is I'm taking the file, and each segment is now becoming a row in my data set. So each segment is becoming a row, and then I associate the audio with that piece of text here. So yeah. Now there's maybe one subtlety here. When you write the segments, which actually happens before setting up the data set, it happens above. Technically, you could add in some padding, which means if you hear audio starting at this word, you could allow the audio to go back a little bit more. I think it's probably not necessary because the word timestamps are reasonably accurate, and I didn't properly ablate whether adding padding would help or not. The problem with adding padding is it can catch part of an earlier word that's not in that segment. The benefit of it is it can also catch sounds that are part of that word if the word timestamp was not very accurate. So you can think about whether you want to adjust the padding before and after. There's a little flag here. The default for padding before and after is 0.2, pad after is 0.25. But I think when I actually set up this, I set it to 0. Yeah, you can see when I call process audio, or rather when I define that function, I set the padding to 0. So for now, there's no extra padding being added. All right, so for setting up the dataset after the cleaning, as I said, it's quite simple. I'm just mapping each segment across to the dataset and pushing up the audio file. There's not a whole lot more to say there. Next, with the dataset ready, and what you need to have is an audio segment less than 30 seconds and the text, that's what it's trained on, and the audio needs to have a start and an end timestamp. We're now ready to do the fine-tuning itself, which will be done with Unsloth. And the first thing to do here is to load up the model. Now, I'm going to, I don't need to rerun this because I've already saved it from running earlier. I'll just comment on a few things here. You can do 4-bit fine-tuning. We're going to do English and for transcription. If you're rerunning again, you might want to delete the model. We're going to use LoRa. We're going to use it on the attention, and we're going to use it also on the linear layers as well. A rank of 32 is probably fine. And I'm going to use RS LoRa as well, rank scale LoRa, which essentially will, relative to not using it, it will increase the effective learning rate of the adapters. Next, we're going to load the dataset. I'm not doing anything different to the Unsloth template here. I'm just loading up the dataset, which involves the audio arrays. The sampling rate is grabbed from the audio, and we convert the audio into features. These are actually MEL spectrogram features. Spectrogram means we convert the audio into its frequency representation, and then we further adapt it into the human adjusted frequencies as perceived by the human ear. That means MEL. So we've got the MEL features, and we've got a tokenizer for the text, and we basically want to prepare the MEL features, which is the audio, and then the labels, which is going to be the text. And that will constitute our data set. We'll have train and validation. And we want to make sure we're in 16,000 hertz because that's the frequency that Whisper works at. And with that, we're ready with our training data set and our validation data set to pass it into the trainer. So you can see we've 7 rows of training. We've got 6 rows of validation. We do need a data collator. This is getting the labels ready. The labels are the targets that we want to compare the predictions of the LLM with, and then we do cross entropy on them. There are some adjustments here to make sure we ignore padding. So if our sequence is shorter than another sequence, we're going to pad out the end, for example, and then we're going to make sure to ignore those when we compute the loss. So we've got a data collator that would be able to pass to the trainer down here. You can see the data collator should get, where does it get passed in? These are the arguments. The arguments get passed into the trainer. Here's the data collator, and the arguments are getting passed in here. We're going to compute a loss, which is the word error rate. There are 2 ways to compute this. One is literally for when you do training, you are predicting a token, an output token that will follow on from the previous token, which is a word. So Whisper is both an encoder and a decoder. It's an encoder because it takes in the MEL features, the sound features, and it's a decoder that auto-regressively produces text. So each token does depend on previous tokens. And when you're in training mode, you are always essentially predicting 1 token at a time. But in training, let's say that the first 4 words are the quick brown fox. Then the question now for the model is to predict the next word, which is going to be jumped. So you're going to grade it on whether it got jumped or not. And it will also have the audio coming in as an input, not just the previous words. It's got the help of the audio too. And that's called teacher forcing, where at every point, so if we move further, the quick brown fox jumped over, and now it's being tested on the word the model is always being given the text history that is correct, the correct text history plus the audio. That's called teacher forcing. But in practice, when we try to transcribe, we would not be giving the correct history at every point. We will only give a start token, and then the model will only be able to rely on the audio input in order to give the correct transcription, not the text history. So the difference between teacher forcing and generative prediction is that in teacher forcing, the model also has the benefit of that text history, and that obviously helps because it's more information. So with teacher forcing, your word error rate will be lower, whereas with generation mode, you're going to have a higher word error rate, because if there are errors in the words, in the early words, that's going to cause divergence later on. So something to appreciate. In practice, it's the generation word error rate that you care about. But if you have very long sequences, then that is going to be high and it's going to diverge. So to some degree, it can be a bit more robust to look at the teacher forced word error rate. But if you want actual performance, then you don't want teacher forced. So this is kind of a technical point, but can help you appreciate why word error rate is going to be higher. The default in this notebook is to use the generative metric, not the teacher forcing. So here we have the compute metrics, where we compute the word error rate. We're then going to set up training. So we'll define an output directory, our batch size. You can probably make that bigger quite easily, especially on an A40. The eval batch size, gradient accumulation steps, and our learning rate. How many epochs? 2 seems to work fine. If BrainFloat 16 is supported, if you're not in Collab, for example, that should be supported. And here you can see predict with generate. That's going to be true if you want to have a more realistic word error rate. Otherwise, it's going to be false. And by default, we do not use teacher forcing. And we are going to do evaluation, and we will train at a constant learning rate. So running all of this with the trainer, you can see the training is proceeding quite well on this data set. The training loss and the validation loss. Well, the training loss is falling a bit more, which is typical. There's a little bit of overfitting, although the last point is kind of higher. That's an anomaly. The word error rate is coming down smoothly, and you can see by even the end of the first epoch, it's come down quite a bit. You maybe get some benefit in the validation loss, 0.5 to 0.4 by doing the second epoch, so probably worthwhile there. And then the question is, how does that perform? I'll talk about pushing to hub in a second. But to determine how it performs, we're going to run a quick evaluation. We'll evaluate using the original base model and then using the trained model. And you can see the results here. So while in the untrained model, it'll say Anthropic Mixtrali by 7B instruct, whereas here it's correctly getting the full stop after Anthropic, and then it's getting Mixtral 8 by 7B. So this is pretty good here. You can see GPT-5 Turbo, it's nice and clean. So there are definite improvements. Now, there are some things that are still wrong. For example, it's not putting a space between WizardLM 1.0 and Spin. I suspect that's because I've only given each word once in the training data set, and the only place that Spin appears is at the start of a sentence. And because things get tokenized differently if they do or don't have a space before them, the fact that it doesn't see Spin self-play within the middle of multiple sentences is possibly causing this issue here where there's a space missing. DeciLM, DECI, is also not being corrected. Possibly it's just not seeing enough data or the right context for getting that. Now, these are really small data sets. If you wanted to properly teach the model, you would need to have the words within probably multiple contexts. I'm guessing like 3 to 5 at least to see some better generalization. But already there's quite a big improvement. And this is really short training. We're only training here for just a few minutes, 36 seconds, in fact, on an A40, which is not even that powerful of a GPU. So this is an evaluation. Before that, I've already actually merged the model, so you can select to either save the model locally here or merge it and push it up to hub. So I've merged it, I've pushed it up. I think it's public. You can find it at Trelis LLM Lingo. If you just go to the same repo as the dataset, but take out the word datasets, you can see the model is here. And because it's the turbo model, it's 1.62 in size, so a fraction of the Whisper large model. And after that's been merged, You can also choose to convert it into OpenAI format. I've just got to stop here. That's why this cell failed. But you could install OpenAI if you want to use the model with OpenAI libraries. Alternatively, if you want the fastest inference, you can save it as a C2 translate model and run faster Whisper. I have this covered in the Whisper Turbo video, so I recommend checking that out. It does allow you to run a server with continuous batching, so that's going to give you the highest speed if you're looking for inference there. This brings us to the end of the training tutorial. As I said, a lot of the training is covered already in the free Unsloth notebook. The main things that I'm adding in here are around the data processing, which is going to be critical if you want to get high performance, and then some tweaks to allow you to run either teacher forcing on the word error rate or not. I'll just finish by emphasizing the value of doing the human review of the data and getting your chunks very clean. This seems to be pretty important. I ran trainings just naively using full segments from Whisper without word-based timestamping, and my word error rate was often up to around 60 or even above 100. You can get word error rate above 100 because if you add in words that aren't there already, that's going to cause the error to be higher than 100%. So with that, let me know any questions on training Whisper models. You can, of course, train even smaller ones like Whisper Tiny. Let me know if you have questions on the dataset generation or on the fine-tuning, and you can find more about the resources down below in the description. Cheers, folks.